And we are live.
Okay, thank you very much. So can I start?
Yes.
Okay, so hello everybody. So as Yuri would say, this is my freedom day. Our last lecture of this course on SRB measures and Young towers. As you can see, there's a new link now with the full set of slides with the 4 lectures. So for today, we have this 4th section on inducing schemes and in particular the applications to non-uniformly expanding maps and partially hyperbolic attractors. So I'm gonna start with a very general framework. So the idea is we use similar arguments when we treat the case of non-uniformly expanding maps and partially hyperbolic systems whose central direction is mostly expanding in some sense. And in many places we use similar ideas. And when I was writing this book on these topics, I realized that I was repeating the arguments. Nevertheless, so you could say, well, simply say it's similar. But at some points, there are some technical points. There are some places where it's not exactly the same situation. And so I tried to find a general framework on which I can adapt both the case of non-uniformly expanding maps and also the case of partial hyperbolic attractors. So I will start talking about this general framework, and then I will apply it to the 2 cases I have in mind. So now the situation is we have a map from a finite dimensional Riemannian manifold, and sigma is a submanifold of M, possibly equal to M. In the non-uniformly expanding case, we are going to apply the conclusions we get here. In fact, sigma will be equal to M. But in the diffeomorphism case, in the partially hyperbolic case, sigma will be a disk in the manifold, a disk where we have some non-uniformly expanding properties in the central direction. So that's the 2 situations we will be applying this. And so we'll consider also M, the Lebesgue measure and Borel sets of that that submanifold sigma. So it can be a submanifold with the boundary if it's a disk. And I will use this n to denote the distance on the nth image of that submanifold. So is the distance with respect to the Riemannian structure on the submanifold induced by the Riemannian structure of the manifold. And also Mn will be the Lebesgue measure on the nth image of the submanifold sigma. As before, so I've already introduced the letter M for Lebesgue on the manifold, and M with the index manifold is the restriction of Lebesgue measure. Okay, so it's said here. So let's start with some assumptions, and then I will deduce out of these assumptions some interesting results. So assume that there exists a disk, can be a subdisk in the case sigma is a disk. So with the same dimension of sigma, such that 3 conditions hold. So the first one is that there is a sequence of compact sets in sigma such that almost every point in that disk belongs in infinitely many H of these sets Hn. So this in practice are sets of points where we see some good expansion in the future. In particular, well, for those who know what it is, this will be sets, Hn will be a set for which n is a hyperbolic time. For those who don't know, don't be scared, I will introduce them, so no problem. So this is the first property. So there are many moments, if you can think in these terms. So there are many moments in such that the points belong to these sets here. The second property is that the points in this set have some good expansion properties, as I said, and I will make it more precise now. So for each point in this Hn, there is a neighborhood of it, so of the point x. I call this neighborhood Vn of x, such that Fn maps diffeomorphically that neighborhood to a disk of radius delta 1, so there is a uniform delta 1, such that it maps to a disk of radius delta 1 around the image. So these are the expanding properties I mentioned. So it expands to a big disk because these VNs, they will shrink. So there will be smaller and smaller neighborhoods of Vn because of an expanding property I will state in a minute. So, and there are constants, uniform constants, such that when we look back, we have uniform contraction. That's what this property says here. See that sigma is a number between 0 and 1. So this is the usual property for that uniformly expanding maps have. So now it's restricted to this neighborhood of the point. And the other one is a bounded distortion property. So for the Jacobian, when restricted to that neighborhood. Okay, so this is for the points in the neighborhood. So points in Hn, they have a neighborhood such that it expands. In particular, when you apply to k equal to n, you have expansion, because when you look backward, you see a strong contraction, sigma to the n, and with bounded distortion of the Jacobian. So this is our second condition. The third one, so as I said, I'm going to apply this to systems with non-uniform expansion in some directions, and the idea is to induce, to use the material I gave you in the previous lectures. And to induce, we will use this feature of points that small neighborhoods, they grow to large scale. So we'll fix some delta 0, and we with some good expanding properties of points on it, and I will use these neighborhoods to grow to a large scale. Delta 1 here, delta 1 in practice will be much bigger than the radius of the disk delta 0. And then we'll use some transitivity of the system to bring that large disk of radius delta 1 back to or close to delta 0. So back to delta 0 when it's an endomorphism, close to delta 0 when it's a diffeomorphism. So that's the general idea. And so the properties we need when we bring the image of the Vnx close to delta 0 is stated, the properties we need for those. There's so using the transitivity in the applications, we'll see there's a uniform number of iterates such that the image of Vn, the nth image of Vn, comes close to the initial disk. And we need this, we can prove in the applications that we have these properties. So there is there is some uniform constants such that the Vn, so the neighborhood of a point in Hn, has the most important one is omega NL. We also need a neighborhood of it just to make some calculations and make some estimates. So just because of that, but the important ones are the omega NL without the tilde. And what are the properties for this omega NL? Is that the omega NL is sent onto a disk of radius delta 0. Okay, so at this moment, I'm not going to say that it returns or not, so that will be done in the applications. But what I need for the first properties I'm going to deduce is just that it's a uniformly finite number of iterates, that after the Vn grows to large scale, there is a portion inside the Vn that in a finite number of iterates goes to some disk of radius delta 0 and goes with some control. I'm not saying anymore that we have expansion, but at least in the iterates in between. So see that this is only, so in iterates in between. So this L, little l, is bounded by the large L, it's here. And so for the iterates in between 0 and this little l, we have some control on the distortion. So we don't make, the idea is that we have expansion on the Fn iterates, and then we don't make big damage on the expansion we had because we have this control. This is particular, this property, if the map has no critical points nor singular points with the derivative going close to infinity, then this property is easily verified. So the problem is that we want to apply to systems with the critical points, derivative, not an isomorphism, and singular points, and so the content of this is especially important in those situations. And also we have some bound on the distortion. See that here the number of iterates is bounded. L is bounded by the capital L. So distortion is, if it's a diffeomorphism, or at least a local diffeomorphism, no critical points, no singularities, this is trivially verified as well. Okay, so these two conditions are important when we have we need to take some care to verify them when we had either singular points or singular or critical points. Okay, so now some notation. In practice we'll be dealing with the sets omega and L, and in some situations it's not important the index, so the time n and the time L. So we'll simplify the notation, and similar so for these tildes, which are small neighborhoods of them, and we'll see it the other way around. So we'll think of the omegas, and then associated to each omega there's a Vn. So I will refer to the Vn as Vn of omega. See that Vn is by definition a neighborhood of the point in sigma, but not necessarily, we don't have necessarily the reference point that we use to build the V, or that we will use to build the Vn, that is a neighborhood. Not necessarily the point belongs in omega and L tilde, and so also not on omega and L. So the idea, as I said, I repeat it, is it grows to large scale at time n, then we bring it back to some region. In practice, that's what we'll do, and we don't have anymore we cannot assure anymore that the reference point will fall into that region, but that's not important at all. Okay, so in terms of applications, Vn will be defined using expanding properties of the system. Actually, it's not the Vn, here is a mistake. So it's the omega and L will be defined using expanding properties of the system for defining the Vn, and then transitivity to bring it back to some region, which will be a disk in the endomorphism case, or an unstable disk when we are trying to build Young structures. So we'll have a disk delta 0 where we build these Vn's, and then a large image comes back to, but not to the disk, comes to some other disk that will belong to the Young structure. So the image of omega and L and the disk delta 0 itself will belong to that Young structure. So that's the way we will build the Young structure, okay, using this result. So, but the first conclusions, it's not important the way we are going to build. Simply assume that we have these sets, okay? And okay, so now some more definitions. So in many cases, typical points in the disk delta 0 belong, and I'm introducing this to this terminology. So positive frequency means that typical points, so there is some definite fraction, theta, such that for M0 almost every point, so typical in this sense, for M0 almost every point, which is Lebesgue measure in delta 0, we have this. So this is the asymptotic frequency in a weak sense, because I'm using lim sup. lim sub bigger than something. So is an asymptotic frequency in a weak sense. And I will refer to, when I change lim sub by lim inf, I will refer to it as strong positive frequency. Okay, so is the frequency of times that the point belongs to the respective h. In the later case, we can introduce this, because if this lim inf holds for almost every point, then this means that for almost every point there is a moment after which this sequence satisfies this inequality. And so we can define this minimum. Of course, this minimum n here, this n0 here depends on the point x, but no problem. So we can define this h theta x. Okay, so this will play an important role in our estimates. So it's a certain threshold after which we have, so in the case we have the strong positive frequency is for a given point as a threshold after which we have some good estimates on the frequency it belongs to the good sets hj or hn. Okay, so our first result that I will give you an idea of these results. It's a very abstract result with these abstract assumptions. So assume that the three properties hold, then we can build in delta zero. See that in delta zero, almost every point has these Vn, so they are neighborhoods of the points, but these neighborhoods, they intersect the other neighborhoods, so there's no assumption saying that they are pairwise disjoint or anything like that. So it's simply for almost every point there is actually by the expansion property, for almost every point there is a fundamental system of neighborhoods of that point. And so out of these neighborhoods, we will build a partition. So the first conclusion is that there is a mode zero partition of delta zero into domains of that type, domains omega and L. Moreover, and I think that reading this statement, you are already realizing what is my intention with this. Setting R as n plus L, so it will be in practice the return time. Well, there are the good properties for instance, in the endomorphism case, to be a Gibbs-Markov map. See that I defined Gibbs-Markov very generally, very abstractly. But then I said, well, when we have smooth maps, we can deduce the properties of Gibbs-Markov, and essentially are these properties. When we take sigma equal to the manifold, these are the properties that imply the existence of a Gibbs-Markov structure. Okay, so is expansion in the future is and the control on the Jacobian of the return map. Okay, but as I said, this is also prepared to be applied in diffuse case, in a partially hyperbolic case, because this sigma doesn't need to be the manifold, it can be a subdisk in the manifold. So this first conclusion is, out of those properties I've stated, we can build some induced map with good properties. And we will also deduce some estimates which will be important. For instance, in this first property, I don't say anything about the integrability of R. In fact, the integrability of R will be a consequence of this second property. So there are sets whose contained in delta zero. In fact, there will be rings around the domains omega and L. I will tell you in a minute how to build them. Such that the sum of this sequence of sets is finite, the Lebesgue measure of them is finite, and this property here is saying that a point belonging to the good set Hn that is not belongs to an element with return smaller than this number here necessarily belongs to one of these sets. So this is a way, what's the idea of this? Is a way of controlling. So in the sets Hn, we will build some, or using the sets Hn, or the points in the sets Hn, we will build some elements of the partition. But because we want it a partition, there will be some conflicts. So there will be a point for which we have an omega NL associated to it, another point for which we have an omega NL associated to it, And so omega and L and associated to those, the omega and L's associated to those points may intersect in a set with positive measure. So we cannot take both points or both domains to the partition. So we'll have to get rid of one of them. And this set S will be a way of controlling the points in Hn that we get rid. So there is still some control that for the points that we do not use to construct the partition. And this is a key estimate that Hn intersection R bigger than L plus N is contained in this Sn where we have some control of the measure. So this second property is essentially to deduce the integrability of the recurrence type. And the last one is an assumption. So is a conclusion, sorry. So if typical points belong with strong positive frequency, so is the property that I've stated before. So if so we know that typical points belong in infinitely many Hns, but if they belong with strong positive frequency, then there is also a very good conclusion. See, for decay of correlations, when we use the inducing schemes, we want to control the tails of the recurrence type. So we want to control modulo this L, which is a bounded number, so it's completely unimportant. We want to control R bigger than L, N. And this conclusion is saying that there is a sequence of sets with the Lebesgue measure decaying exponentially fast to 0, such that the tail of recurrence times is contained in the tail of this, and this is related to the strong positive frequency. So this is that points which have a threshold, as I said, H theta is a certain threshold after which we have some good property. So is the tail for that threshold for points with strong positive frequency. So this says, and union with this, but this decays exponential. So the En decays exponentially fast to 0, the Lebesgue measure of it. So essentially, this says in the applications we have in mind, which are for polynomial tails and exponential or structure exponential tails, this says that the decay of the recurrence times is essentially given by the decay of this H theta bigger than N, because the other part decays exponentially fast. And so that's the idea of this conclusion. So to induce, to prove the integrability, and to have some knowledge on the recurrence, the decay of the recurrence types. Okay, so an idea now of this construction. Well, this construction, the approach here is related to, well, we use these ideas, as I said, in many situations, in endomorphisms, diffeomorphisms, and in writing my book, I decided to put this in this abstract setting that can be applied to all the situations we consider. So the situations are here mentioned in these papers, and they are all based, well, I'm a co-author of all these papers, and the ideas are all based in very nice ideas from Guezel that apply this in some particular, well, in some situation with having in mind to prove decay of correlations for the Vienna maps. And then we use that idea, those ideas in more general situations, and that's the ideas I'm going to present now. So we are going to define inductively these objects, Pn, delta n, and Sn. The Sns are those that have already been mentioned in the conclusions. Well, the Pns is the family of elements in the partition constructed. So there will be an inductive construction. So are the elements in the partition, for the conclusion of the theorem, constructed in step n, at step n. Delta n is the region that after the nth step, so we have the elements constructed up to step n, is the region that the set of points that are still not belonging to an element of the partition. So is the part that remains, is actually the set R bigger than n. And Sn, so Sn is the set, is the Sn that I've already mentioned. So it contains points, as I said, it contains the points in Hn that are not taken in the elements constructed for the partition until time n. Okay, so these are the ideas for these elements. And a key conclusion is that a point in Hn either belongs to an element of the partition or to an Sn. Okay, so let me start by telling you the main ideas of the construction of this partition. So it's an inductive construction. So I'll describe the first step. The other steps are quite similar. So we start with a large n0. So we consider hn0. Well, hn0 is a compact set by definition. So and the points in hn0, they have the vn0s by assumption. So we have a finite set such that hn0 is contained in a union of a finite number of elements of the type vn0x, because these are neighborhoods of points simply by compacity. So we consider these points in this finite set, and for each there is these neighborhoods. So the neighborhoods that go to a disk of radius delta 0, the delta 0 given in I3. Okay, so we consider these elements, and for Pn0, what is, let me, oops. Oh, I have, let me just, well, this doesn't want to be, okay. So we take Pn0 as a maximal family. So these are, look at this picture, these are the reds. So these are elements omegas with certain indices. And so these are the omegas, the red ones, the elements in Pn0. So we take a maximal family of pairwise disjoint sets of that type contained in delta 0. They have to be disjoint. So we take them I take a maximal family. Why a maximal family? Because if there is one that at the n0 belonging, so if there is some other element belonging with associated to a point in hn0 that is not taken, it means it necessarily some that has been taken. So the idea is, so we take the reds, full red, and then there are those reds which are not full red that could be taken. But since you are taking maximal family of pairwise disjoint, we cannot take the other reds which are not full red. But see, they intersect, necessarily they intersect the reds that we take. For otherwise, the family will be maximal. And we define the SNs. So the SNs are small neighborhoods of the elements that we construct. Actually, not neighborhood, because these are some rings around the elements, because they do not contain. So this is the reason why, because the reason why I have to introduce the tildes is because I want to make estimates. And if I take only the omegas, I couldn't make estimates out of omegas. So this is to make estimates in the neighborhood of omega. So that's why I introduced the tildes. And so the SNs are neighborhoods of the domains that I construct. And these neighborhoods decay, they will decay, the measure will decay exponentially fast. So that's why the sum is finite. And we also need to take neighborhoods of a neighborhood, in this case, of the boundary of this delta 0, because I want a partition of delta 0. For instance, this element here, this red not full, I cannot take it because it goes onto a disk of radius delta 0, but the part inside this delta 0, not necessarily, because I need to take also a part out, and that won't be a good domain for the partition of delta 0. And for that reason, that's the reason why I consider also a neighborhood S of the complement. So this is a neighborhood inside delta 0. Okay, so that's this ring here around the boundary of delta 0. And so I define the SN0 as the union of these domains. So the domains around the domains that I take for the partition, and also around the boundary. And I take delta n0 as the part that has not been constructed, that we do not take to the first step of the construction. And for that definiteness, we take also delta n and Sn as delta 0 for the n's less than this n0. This is completely important for estimates because the estimates are all asymptotic. So this is just a finite number of n's. Okay, in the general step, we do is the same idea. So we take a maximal. So, but now is a maximal family of pairwise disjoint sets in the part that has not been constructed until time n. So now I take some n bigger than n0, and this is maximal, not intersecting. So now is not before it was not intersecting the other ones at that step. It was the only step. Now I have to be sure they do not intersect the elements constructed before. So that's what I have here in this union. Okay, and then I take delta n as the complement of it, and I also take the rings around the domains that I construct exactly in the same way. But there's only something here that I want to highlight, is that for each element that I constructed before, in time n, I take also a neighborhood of it, but of order, so decay exponential fast, but of order n minus k. So it means that, for instance, when we go to step n plus 1, around this red here, I will consider Sn plus 1. It will be smaller than the Sn I've taken here. Because here I take n0, in the other one I will take n0 plus 1. Okay, so that's the way. So we define these neighborhoods not only for the elements we construct at time n, but for the elements that we have constructed before. Okay, and then so this is the way we construct this. And then we have some metric estimates. I'm not going to make calculations here, but we have this key property. So this key property says the sets in H, that's the point that we can control, that are not taken at time n for the construction, they necessarily are in the set Sn. And also the set, the measure of the sets Sn. So we fix omega in pk, and then we have the Sns for n bigger than k, as I said before, but the Lebesgue measure decays exponentially fast. And so that's the reason why we can control the sum of the Lebesgue measures of these Sns and see that it is finite. And so for that reason, we'll have that P is a partition. So P is the union of all pk's. So this will be a partition. Why that? Because of the first property. So if a point is not taken for the construction, then it belongs in Hn, it belongs to delta n, and belonging to delta n necessarily is in Sn. So since the Lebesgue measure of these Sns is finite, Borel-Cantelli lemma says that a point can belong, or typical points belong only to a finite number of Sns. So since this holds and typical points belong only to finitely many Sns, necessarily at some point it will be taken for the construction. So the fact that it's P is a partition mode 0 is a consequence of lemma 4.4 and Borel-Cantelli lemma and lemma 4.2. Okay, so we also want the integrability of the recurrence times. And so we define for this partition, we define the recurrence time as I said. So Rn plus the L that is given by the third property. We have this property. This is because of the construction. The construction we just made gives this property. So the conclusions of the first item follows from of the theorem we are proving. They follow from the conditions I2 and I3. So the first item is that it has expansion and boundary distortion. So it's essentially composing the expansion we have here with some estimates that say that the distances are not damaged in the last L iterates. And that's why we take N0 very large to have some big expansion from here and then compensate this possible non-expansion in the last L iterates. The second item was this estimate here. Essentially is this, well, is exactly this estimate. So this is because of the construction. The third item is the most technical. So let me show you the items for you to see what the third item is this one here, and is technically very involving. So I'm not going to even give an idea of this construction. This is where we use the ideas of Guesel. If you want, you can see in this section that I mentioned here. Okay, so the integrability of the recurrence times. So I said that this condition, which corresponds to the second item of the theorem, so corresponds to this 48, this condition is related to the integrability of the recurrence time. Now I'm going to give you an idea of that integrability, which is important. So this will be used to build, as I said before, either Gibbs-Markov maps or Young structures. If it's Gibbs-Markov, in both cases, we have associated, so in this case, we have a Gibbs-Markov map. But even in the case of Young structure, we have a Gibbs-Markov map associated, because we have seen in the last day that we have a return map for the Young structure, and then we have a quotient, which is a Gibbs-Markov map. And if we consider the sequence of consecutive recurrence times, we say that the sequence of sets is F. So this is a sequence of sets which will be of this type in practice. Let me tell you that in the case A, so we have two cases that we have in mind to apply. In the case A, that's this footnote here. In the case A, the sets Hn star will be exactly Hn. Okay, so there's no mystery about them. In the case where we build Young structures, it's not exactly, it's close to it, and I'll tell you when we consider the partial hyperbolic sets, partial hyperbolic situations, and but will be a type of set with the nature of HNs. And the idea is that this property in case A, this property, when you take Hn star equal to Hn, this property will be true. It will be a consequence of the definition of the HNs that we will consider. So this property 49 will be a consequence in case A. In case B, we need to introduce the new set in order to have this property. Okay, so it's a bit mysterious for a while. I'll let you know later how these sets appear. But so assume this property now. Assuming this, so property is being F concatenated. So we have this proposition. So assume that we have a Gibbs-Markov map with respect to a certain partition and with certain recurrence times. Assume that we have a sequence such that typical points in delta zero belong in this sequence of sets with strong positive frequency, as I said before, and F concatenated here. And a sequence Sn such that the sum of the measures is finite, and we have the property that we have just obtained. Then R is integrable with respect to M0. So how can we prove this? Well, the proof is the following: is by contradiction. Assume that R is not integrable with respect to M0. Well, M0 associated to the Gibbs-Markov map, we have a measure which is equivalent to M0. And so if it's not, we assume it not integrable with respect to M0, we can assume it not integrable with respect to this invariant measure. The advantage of this invariant measure is that we can use Markov theorem. And so using Markov theorem, we can prove that this limit, Markov theorem can be used also for non-integrable functions, provided the function is non-negative. That's the case of this. And so we have that this limit is equal to infinity. Well, we know, I've already mentioned that this is true. And so from Borel-Cantelli, a typical point belongs only to a finite number of SNs. So set for each, for these typical points, set S of X as the number of times it belongs to the SNs. Well, we also have, it's not difficult to see, that the integral, so we have this function which is non-negative again, and using again Markov theorem, we have this, and it's not difficult to see according to the way we have defined the function that this is precisely this. And so, and this is summable because it's summable with respect to M0, and nu is equivalent to M0 with the density bounded from above and below. And now this is the point, the only point where I use the fact that Hn star is F concatenated in Hn. This is to deduce, I'll leave it as an exercise, to deduce that the set of J's for which in between two consecutive returns belongs to H star is bounded by 1 plus S of Fj. One is the fact that it may be in one element of the partition, or there's a certain number of moments it belongs to the Sn. So that's the idea of this estimate. And so given, now set Rn as the minimum Ri for which Ri is bigger than n. So now we can, using the estimate in the exercise, we can prove this, that this, so using these Rn's, we can prove that, so it's divided into the iterates in between consecutive returns. So we can see that here is from 1 to n. So here it was from Ri to Ri plus 1. So from 1 to n. So we divide into the various return times that we have. And then we can say, so using the estimate, we can say that this is bounded by this. And so this is bounded by R plus the sum of the S of Fi's. Okay. So therefore, now we divide by 1 over n. And I have this estimate. So this is exactly using the previous estimate, and then making some arrangement here. I put Rn in evidence, and then I make this arrangement. And then observe that if Rn is equal to k, by definition, we have this. And so we have this estimate here. It's a trivial consequence of that. So we have that this limit here is the limit of this. So it's using that. So this bounds here, we usually deduce this, but now this is equal to this. This is the fact that it's not integrable with respect to nu, the R. Well, and this is infinity. So we get to the conclusion that the limit of n over Rn is infinity. So it follows from the estimates that we had before, this limit and so on. So this is finite. When you divide by 1 over Rn, this is finite. So we have that this limit is equal to 0. Well, but this is I said a frequent sequence. A frequent sequence means typical points have positive frequency on it. So it contradicts that, because the definition is that the lim sup of this is positive. So here I'm proving that the limit is 0. Okay, so that's the way we prove the integrability. So this is a very nice argument. This argument, let me tell you that this argument is used by Pinheiro in a situation of non-uniformly expanding maps. Actually, I think he has seen this argument in the book of the Mello and Van Strien, which actually used some argument in one-dimensional dynamics from, I think it's from Keller. So in the end, this argument comes from Keller via Van Strien, the Mello, Van Strien, and Pinheiro, and we use it a lot in the integrability to prove the integrability in many situations. This is a very nice argument. So let's go now to the applications, and now I will be first applying to non-uniformly expanding maps, so endomorphisms, and possibly with critical or singular sets. And I'll consider local diffeomorphism out of a set that will be possibly a set where derivative is not an isomorphism, so it's a critical set, or a set of points where derivative simply does not exist. That's what I call singular set. Okay, or even the boundary of the manifold, if it's a manifold with boundary. So it's a bad set of points. Okay. So out of it, it's a local diffeom. And we assume that this bad set of points is non-degenerate. Non-degenerate means, first of all, that the Lebesgue measure is 0, and these three conditions hold. So I won't look in many detail to them, but the first one says essentially that F is in some sense is the push forward of Lebesgue is non-singular, is non-singular with respect to Lebesgue measure. So if a certain set has 0 Lebesgue measure, then the pro-image and the image is 0 of that set is also 0. And also these two other properties essentially are saying that when we go close to the critical set, the derivative behaves as a power of the distance. This property is true in many situations, for instance, for non-flat critical points in one-dimensional dynamics, for the critical points in Vienna maps. So these are abstract conditions actually introduced in my paper with Bonatti in Vienna. We introduced this in order to generalize many examples as a class of non-uniformly expanding maps in any dimension. And so these are the properties we need. Okay, essentially saying that sets of Lebesgue measure 0 are preserved, and near the bad set of points, critical, singular, the derivative behaves as a power of the distance to that point. And now the non-uniform expansion. So non-uniform expansion is this condition here. So we say that it's the map is non-uniform expanding on a certain set H, if for some choice of a Riemannian metric on M, we have this condition. What is the condition? Well, first look at this condition here. So this is saying that derivative, the inverse of the derivative, so lambda is the positive number. So we have log here. So this is saying that log of the inverse of derivative, if it were only this, not the average, if it were only this, the log of the derivative would be smaller than the number negative. If you take the log, take out the log, this says that the derivative is smaller, the norm of derivative is smaller than 1. Well, this is the usual condition to define uniformly expanding maps. For uniformly expanding maps, instead of taking orbits, and so here we have an average along orbits. Instead of taking average, we say that this is true for all x, and that's the usual definition of expanding map. So here we are saying that we have that condition in average and in a weak sense. It's not the limit, it's only lim-inf. See that if I replace here lim-inf by lim-sup, I obtain a stronger condition. This will be used as an assumption. So this assumption is better. I'm taking lim-inf, saying lim-inf is smaller than some negative number is weaker than saying that the lim-sup is smaller than that negative number. I will use also lim-sup later for other purpose, not to construct the SRB measure. So I will use this to construct actually the inducing scheme and the SRB measure. And for the decay of correlations, I will need the stronger condition. And since we want to consider situations where we have critical or singular sets, we have a price to pay. And the price is to impose a condition on slow recurrence to the critical or singular set or the bad set of points C. And slow recurrence is this condition here. It essentially says that we can go close to the critical set, but not too close too fast. So in average, we have some control on the way we go close to the critical set. Let me say that this condition is also, it holds in, for instance, for Vienna maps, for quadratic maps, for many well-known one-dimensional maps, this condition holds. So this was deduced, for instance, for quadratic maps from Benedict-Carlson conditions. Freitas proved that this condition holds. So it also holds in the case of Vienna maps. So it's a natural condition in these maps, in this situation of maps with the critical points. And there is a distance here, which is not a true distance, is the truncated distance which is defined in this way. So is the real distance if the point is close to C. So, and is 1 if the point is not close to C, and close is close distance R. And see that since we are taking log here, when it's 1, it doesn't count anything for this average. So when we are far distance R from the critical, from the set C, I'm not going to call it critical because it can be also singular set or the boundary, from the set C, from the non-degenerate set C, we simply do not contemplate this in this condition. So this is to say that we are only taking these averages when we come close to the criticals, to the set C, okay? So, and now we come to a very important concept in all these results on non-uniformly expanding maps, which is the notion of hyperbolic time.
Isaac,
so, yes?
Can I make a quick analogy?
Yes, sure, please.
But I believe that this kind of slow recurrence is also related to what appeared in my mini course.
Your measures, yes, it is. Yes, I don't remember the name you've given it.
The adapted measure.
Adapted measure, yes, it has to do with that. So is the integral. So if the measure is ergodic, then this is the limit is precisely the integral. Is your definition, okay? See that this is the tail. See, since we take adapted, it means that the integral of log of dist is finite, right?
Yes, yes.
Okay, so if the measure is adapted, then this condition holds. Condition 55. Thank you, Yuri. It's a very nice remark. So if the adapted it holds, but with respect to almost all points, with respect to that measure, okay?
Exactly.
Because this is the tail of the this converges to the integral of this function. But since you are taking here this R, this is essentially the tail of the integral. I'm assuming that the integral there are poles in the function, and so this is the condition that gives the integrability. But the problem is that at this level we don't have any measure. So I want to build a measure. I want to build an SRB measure. So this is a condition that I'm going to assume on a certain set H that will have positive Lebesgue measure. This will be my assumption, okay? And Lebesgue measure, unfortunately, is not invariant a priori, okay? So actually, in many cases, it's not invariant at all. So we want to build another measure which is well related to it, and these are the SRB measures. But we need to put this as an assumption, and it's of course related to what the measures to the condition that Yuri used to define the adapted measures. Okay, so let us now consider diffeomorphisms out of a non-degenerate set. We fix some small constant which appears here, but it's completely unimportant. And it's only important when we go to make the calculations, and that's not the case here. Sometimes I put certain things that it's only to facilitate if you want to go to check the calculations exactly the same quantities, and you don't have to be adapting what I said here to what is there. And so so B here is some constant which is completely unimportant here. And we say that n is a hyperbolic time for a point if this condition holds. And what is this condition? This is slightly stronger than saying that this holds for all k between 0 and n. This implies in particular that when you go from, so you have the point x, you have the nth iterate, and you have a kth iterate in the middle, in between 0 and n. And this in particular implies, this is chain rule, this condition here, implies that when you look backward from the fnth iterate to the kth iterate, which is before n, the derivative of the inverse is contracting, because derivative of the inverse by the chain rule is precisely this product here. And so this is smaller than a number smaller than 1, so it's contracting. So this condition of hyperbolic times is saying that it contracts when you you go 1 iterate before, 2 iterates before, 3 until 0. So when you look backward on all iterates, you are you see good contracting properties. So this is a property that uniformly expanding maps have at all points, at all moments. So I'm here introducing a concept that says for certain points, at certain moments, we have the good property of backward contraction. So the points for a certain point, the good moments, that's what we call hyperbolic time. And so this is the case when, for instance, we have a global local diffeomorphism. If it has a non-degenerate bad set of points, we also need to impose some, again, is a condition on not going too close to the critical set. And using this, this is the content of the next result, which, so this was firstly proved in my paper with Bonatti and Viana. We proved that given lambda, if these conditions hold, and these are the conditions which are assured if we assume non-uniform expansion and slow recurrence, okay? So assume that we have non-uniform expansion and slow recurrence. So for big N, for most points in a certain set, we have these two conditions. And so the conclusion of this proposition is that then we have hyperbolic times with certain constants. So this is a number. The important thing is that e to the minus lambda before is a number smaller than 1, okay? And so we have hyperbolic times. And with a good property, there is some theta 0 such that the fraction of hyperbolic times until time n is bigger than theta 0. This is a very important property of these hyperbolic times. There is some technical point, is that there exists. So we have, the idea is to apply, of the proof, is to apply this Please lemma, which is a merely number theoretical lemma due to Please. That many people have used this Please lemma. And the proof is very simple, and using this, if the conclusion were only so if hyperbolic time did not have this second condition, and let me say this second condition in the definition of hyperbolic time, we get rid of it when we have a globally local diffeomorphism. So we don't consider this, and so we simply forget this part as well in the conclusion when we have globally local diffeomorphism where there is no bad set of points, okay? And so if it is only this first condition, the existence of hyperbolic times is a straightforward application of Please lemma. The problem is when we have the bad set of points, C, then we have to use this condition as well, and we have to use it in 2 moments, and so that's why we use this epsilon 1, epsilon 2, but for the conclusion is completely unimportant. So the idea is to obtain the first condition with a certain frequency, and then using the second one, and then adjusting the frequency of the second condition in such a way that the frequencies of both, the sum of them is positive, is bigger than 0, or the sum of the frequencies is bigger than 1. So we can obtain points for which the two conclusions on the two conditions that define hyperbolic time have some positive frequency. That's the idea of this epsilon 1 R1, epsilon 2 R2. So it's applying this Please lemma in 2 moments in order to change the frequencies for which of the moment. Okay, so hyperbolic times for hyperbolic. So if we have these conditions which are related to the definition of non-uniform expansion and slow recurrence, we have hyperbolic times with good frequencies. And the conclusion is then on points having hyperbolic time. So if we have a point with hyperbolic time, then there is a neighborhood. And I guess this is well known to you, because this is my first requirement on on the condition, the very first condition I've presented you today, the condition I1. So, sorry, is I2. It's not the very first, it's the second one. The very first is that typical points belong in in infinitely many HNs. And for the points in HN, we have this neighborhood. So this was the second condition. And now I think there's no mystery of what will be HN in applications. HN will be the set of points which has N as a hyperbolic time. If that happens, then we have this conclusion. So this is something we have deduced in that paper of 2000. So it's a very nice feature of the hyperbolic time. So they have these neighborhoods that grow to large scale. And so we have backward contraction. That's what this condition here says. The uniform backward contraction, and also some bound on the distortion. Okay, so these are properties that uniformly expanding maps have everywhere, every moment. So here we have these features of uniformly expanding maps for points in certain moments. Okay, and so using this property, we can obtain a first result. It's a very nice result, which is this one. So assume we have a local diffeomorphism out of a non-degenerate set, and assume that we have non-uniform expansion and slow recurrence to C on a set with positive measure. So we have the good conditions on a set with positive Lebesgue measure. Then there are transitive invariant sets. These are kind of attractors. So transitive, in some sense, attractors, and you will see that they have some attracting property, such that for M almost every point in H, the omega limit set will be, the omega limit set will be precisely the omega J. So the assumption is we have a set with positive Lebesgue measure. We assume that we have non-uniform expansion and slow recurrence on that set, and then we can decompose. So think of the omega limit points of points in H, and I'm telling you, there is a finite number of transitive pieces that attract almost all points in H. So this is a decomposition of the attractors for the points in H, a finite number of transitive pieces. And moreover, on each of these transitive pieces, there is a ball. See, H, I'm not giving any topological property of H. It's only positive Lebesgue measure. And I'm telling that inside the omegas, the attractors for the points in H, this is always for almost all points, there is a ball. So these attractors contain balls. And on that ball, the map is still non-uniform expanding and has slow recurrence for almost every point in that ball. I'm not going to tell you more than I will say right now for this theorem. The idea is to use these VNs, so these neighborhoods constructed in the previous proposition, and using these VNs, we can, for points in H, we can build smaller and smaller neighborhoods with more and more, a kind of Lebesgue density theorem. So smaller and smaller neighborhoods with bigger and bigger proportion of points in H. And so when we look to the image, we see disks of radius delta 1, for which the proportion is essentially the same because we have a uniform bounded distortion condition. So with this set with positive Lebesgue measure, we can build balls of a uniform radius, delta 1, on which the proportion of images of points in H is close to 1, arbitrarily close to 1. Well, and so we take accumulation points of these balls, and we have a ball on which the proportion is exactly 1. So the idea for the proof, for a first step of the proof of this theorem, is to construct these balls when we have Lebesgue almost every point with non-uniform expansion and slow recurrence. And then we use some decomposition argument. If these balls interact, they then belong to a same transitive piece, and so we can decompose the set of omega limit points into a finite number of those pieces. Finite number because this delta 1 is uniform, so the radius of these balls is uniform. So he uses very nice ideas from a paper of Pinheiro, where he considers expanding measures, a paper from 2011, Wilton Pinheiro. And in Pinheiro, it's not stated like this. We also, we are still only considering the case of non-uniformly expanding maps. This has been, so it has, we'll see it today, it has a similar situation in the case of partially hyperbolic attractors. And I've proved this theorem with Pinheiro, Carlo Diaz, and Stefano in the case of partial hyperbolic attractors. So this is just an adaptation of those ideas formally from Pinheiro to this situation. You can see this in the book. So, so this theorem says that having a set on which we have, so assuming non-uniform expansion and slow recurrence on a set with positive Lebesgue measure, we have these transitive pieces with containing balls where we see the non-uniform expansion and slow recurrence. And these balls are contained in the transitive sets omega. Well, so let's look at these transitive pieces now. So almost everything I'll be doing now is with respect to a transitive piece containing a ball where we know that we have non-uniform expansion and slow recurrence. So after this decomposition theorem, it's natural to consider it. So let omega be a transitive set and omega and sigma be a ball, as in the previous theorem. So it's a ball for which we see a non-uniform expansion and slow recurrence to the bad set of points. So see that the non-uniform expansion is almost everywhere. So let H be the set of points for which we see the non-uniform expansion and slow recurrence. So the measure of H is exactly the measure of sigma. So I'm going to now present you the HN. So I'm now approximating the assumptions of our first theorem today. So I'm going to introduce now the HNs, and I think there's no mystery for you, the HNs, and checking the assumptions, okay, of I1, I2, I3. So I1 is the HN. So the HNs are naturally the set of points that have hyperbolic time at time n. See that proposition, the proposition that we have just seen, gives us the positive frequency of points on belonging in the sets HJ. Okay, so that's a conclusion of the the proposition is not the last one, is the one but last is the proposition on the existence of hyperbolic times. It gives this frequency, and see that it gives see that assuming non-uniform expansion. So this is the weak condition of non-uniform expansion. We have infinitely many moments for which this non-uniform expansion and also slow recurrence. We have infinitely many moments for which this holds. And so we have infinitely many moments n for which we see a positive frequency until n. But then it may happen that for a long time we don't see any longer the positive frequency, but then it will eventually arrive a new moment on which, when we look backward, we see a positive frequency of order, the same theta at that time, and so on. Okay, so there are infinitely many moments for which, when we make the frequency until those moments, it's a definite fraction theta. Okay, so this is the weak condition lim sup. So it says that we have this lim sup. Okay, so there are infinitely many moments for which these fractions are bigger than theta. In particular, if this holds points in sigma belong in infinitely many HNs. And so we have the validity of the first condition that was belonging to infinitely many HNs. Well, and the second condition was the condition on the VNs, the existence of the VNs. Well, the condition on the existence and the conditions are stated precisely in the proposition on the existence of these VNs. So the condition we have just seen. So this is I2. Well, for I3, I'm not going to tell you how to build this in the non-uniformly expanding case. Just the idea. The idea is to use the transit. So this is the point where it's important to be considering this situation in a transitive set. Because with the Vn, so we have some disk, delta 0, which is, delta 0 will be a subset of sigma. So we have some disk. Typical points have the Vn's infinitely many times. So in the Vn's, they grow to large scale. We take this with this delta 0, a disk with very radius much smaller than delta 1. The delta 1 is that for which the radius of the ball's image of Vn. Okay, so we take delta 0 much smaller than delta 1. So delta 1 is defined a priori. Now I'm going to choose the ball delta 0. So I choose the ball delta 0 with radius much smaller than delta 1. And then using the transitivity, I can, in a finite number of iterates and uniform, that's an important feature, bring any ball of radius delta 1 to cover the ball delta 0, provided I take delta 0 sufficiently small. The radius of the ball delta 0 sufficiently small. And so I can see inside the domain a subdomain such that what is the property for this subdomain that we need is this one here. So I can see a subdomain that satisfies this property. So is essentially the property I3 that we need to apply that theorem is essentially using the transitivity. Okay, and so with this, we on these transitive sets, we have the conditions that we need to apply theorem, the very first theorem of today. And then we set the recurrence times as they should be. And we obtain, so C, as I told you in the beginning, I said, well, I'm just putting these conditions I1, I2, I3. For I3, I'm not assuming any recurrence property. It's simply a finite number of iterates more. But now I want to build Gibbs-Markov. So that's why in this case, I'm applying I3 with this extra assumption, returning to the disk delta 0. And so since I'm constructing this omega n else with this property of being returning to the disk delta 0, we obtain a Gibbs-Markov map. So this is exactly the conclusions of the theorem. So this is theorem 4.1, so it's the first theorem of today. And see that by definition of hyperbolic time, this is very easy to check. This is because it's a concatenation property because of the property that defines the hyperbolic times. So if we have a hyperbolic time, so it's backward contraction, and we go to the middle, Fj also has n minus j as a hyperbolic time because it's the backward contraction. Okay, so we have that Hn is Fr concatenated in Hn. So as I told you in the endomorphism case, I'm using exactly the same H, not Hn star as a. So Hn star is more general. So in this case, I can make a choice of Hn star exactly equal to Hn. So these sets Hn, as we have seen, they have so points, typical points belong in them with positive frequency, and also they are Fr concatenated. So these are the conditions to ensure that this R is integrable. So this was the content of proposition 4.6. Okay, and so applying it, we have this nice theorem. So assume that we have a non-uniformly, so a map, which is a local diffie out of a non-degenerate set, and assume that we have a transitive set. So if F is non-uniformly expanding and has slow recurrence on almost every point of a ball contained in the transitive set, and these balls exist, motivated by the previous theorem, then F has a Gibbs-Markov induced map with integrable recurrence time defined on some sub-ball of the ball sigma. Okay, so, well, a first version of this result. So the conclusion is existence of a Gibbs-Markov map with induced map with integrable recurrence times under very general conditions. So a first version of this result was proved by Pinheiro under. So this is a local version, local in the sense that we are restricting to transitive sets, which are actually can be seen as the transitive pieces of attractors for non-uniformly expanding maps. And Pinheiro, so this uses a local construction in some sense similar to what Pinheiro did, but he did with a global construction on the whole manifold. So this is a local version of that result, which is, in terms of applications, is better because we can apply more situations. So we don't have to have the global assumptions, okay? As a consequence of the results we have seen for maps with inducing schemes in the endomorphism case, is that, so under the same assumption, so the same situation and same assumption, so if we assume that F has non-uniform expansion and slow recurrence on a certain subset of points, then there will be these disks, and then applying the previous result, F has a unique ergodic SRB measure whose support coincides with sigma. Well, that it has an ergodic SRB measure is an immediate consequence of the fact that it has a Gibbs-Markov induced map with the integrable recurrence time, plus what we know for maps with integrable recurrence times, the endomorphism case. So if we have an induced map, then the original dynamics has a measure which is ergodic and absolutely continuous with respect to Lebesgue measure, which in this case of maps with no contracting directions is what we call SRB measures. The only plus here is the support coincides with sigma. Well, for this, we use the fact that sigma is transitive, okay? The transitivity allows us to conclude that the support is the whole attractor, okay? So we have this very nice consequence. So if in a transitive set, we have non-uniform expansion and slow recurrence on some set of Lebesgue measure, of positive Lebesgue measure, then there is a unique ergodic SRB measure supported on the attractor. And so this finishes the construction of SRB measures in the endomorphism case for non-uniformly expanding maps. See that I've already said, I'm stressing the fact that here we have a weak non-uniform expansion condition. Let me say that the conclusion on non-uniformly on existence of SRB measures for non-uniformly expanding maps in general. So this is in any dimension. Was firstly proved by myself, Bonatti and Vienna, but in our assumption was stronger in the sense that in the very first result we had lim sup and not lim minth. And it's interesting because we use that, to prove with limits, the idea I've just given you, we use this inducing scheme. So we have these structures, these geometric structures on which we control these recurrence times. We build these induced maps with very good properties. The original idea under the stronger assumption was simpler. We're simpling that using that idea of iterating Lebesgue measure and controlling the densities, at least at some iterates at some subsets. So, and the method gives much less information. Of course, to build an absolutely continuous invariant measure, it was enough and it worked and it was very good. But gives much less information than this new method gives. And it's interesting because this new method is applied under a weaker assumption. So we improve the original result from 2000. Under a weaker assumption, we will obtain more. So this method, in some sense, is more efficient. Okay, what in fact is more efficient is our knowledge on these non-uniformly expanding maps. So 20 years have passed, so it's natural that there are improvements. Okay, so now next goal. Well, decay of correlations. Unfortunately, with these assumptions of non-uniform expansion only and slow recurrence, we cannot say anything on the decay of correlations in general. So we need stronger assumption on non-uniform expansion. But the stronger assumption is not so weird. It's exactly the assumption I used in my paper with Bonatti and Vienna. So we change now lim inf to lim sub. Since this is less than negative, well, less than something, so lim sub is a stronger assumption, okay? So clearly, strong non-uniform expansion, so I use this S and UE for strong non-uniform expansion, and this implies clearly non-uniform expansion. But what is the advantage of this condition? Is that it allows us to introduce this function here. Why? Because this says if lim sup is less than minus lambda, this holds for all points in a certain set. And in applications, I will assume that this certain set has positive Lebesgue measure. So this says that for the points in this set, there is a moment after which these averages are always, so the averages here are always smaller than minus lambda. So this is just the definition of lim sup. So for points in H, we can define this E of X. So X in H, we can define this E of X. This is the minimum, the first moment after which these averages are smaller than epsilon. This is assured by the fact that we have lim sup. So there's a threshold for every X in H, there's a threshold after which we have the averages, good averages in a certain sense, satisfying this. In particular, we have the positive, so this is the condition. Of course, think by now of maps with no non-degenerate critical sets. So assume that it's globally a local diffeomorphism. So if it's global diffeomorphism, so if we have this condition, we know that for every n bigger than this capital N, for that point X, we have positive for all. We have positive fraction of hyperbolic times when we look back. So this gives the strong points belong with strong frequency to the set Hn that we have just built. Well, in the case we have a non-degenerate set, we also need to consider the other assumption. And it also allows us to introduce this minimum for which this is satisfied. And so we have the two conditions, this and this. For the point X, we know that for all n greater or equal than this, the minimum, or the maximum, or see that, well, again, this is a technical point. As I said, we need, in the existence of hyperbolic times, we need to consider two. And so technically we have two functions. And so when we define this, I'm going to introduce this function Hn of X. And so I had to take into account the two, R1 and R2. And so I take the maximum of the three, also this one here above. And so, this is here, I'm saying that when C is the empty set, then is exactly only the one above. And so this function plays an important role in the next result I'm going to present. So what is the result? So assume that we have C1 plus something. See that the plus something is important in the conclusions of the lemma that gives us the VNs. This is to control the distortion. So we need more than just C1. In many of these things, I would say in most of these things, we need more than just C1. In the C1 world, there are many weird phenomena. So we have to to take care of them. And so we usually put more than just C1. So assume it's C1 plus holder local diffuse out of a non-degenerate set and a transitive piece again. If we have a ball such that the transformation, the dynamics is non-uniformly expanding and has slow recurrence to the non-degenerate set almost everywhere in that ball, that's what this says, then there is an L. L is not so important, but there is an L and a Gibbs-Markov induced map defined on a sub-ball. Well, the conclusion on the existence of a Gibbs-Markov we already know because we have deduced it under weaker assumption, not necessarily strong, but new. It was one of the previous theorems. So the good part now, or the new part now, is what comes next, in such a way that this holds. And this was precisely the conclusion of, was the one of the conditions that we have So this is a conclusion. This is a conclusion. And this appeared before. This conclusion appeared before, or something similar appeared before when we were in our very first theorem. So in our first theorem, the conclusion was here. So I was a bit confused now. The conclusion was here. So in our very first theorem of today, it was theorem 4.1. We had this conclusion. Okay. So what was H theta? H theta was the strong positive frequency of points in Hn. And clearly, the condition is this. The condition is this one here that I'm not being able to highlight, but I don't understand why, but that's what happens. So the condition is this one here. So, and clearly, if n is bigger than h, this capital H, well, this for writing is not a problem, for saying is not very good, the notation. So this is the HH I introduced before. So this is to say that H theta is the one introduced in theorem 0.1 is bounded by this HH. So the conclusion of our first theorem of today gave us this. And what I'm telling you now, so applying theorem 4.1, we obtain a Gibbs-Markov induced map. That's what we obtained before with this condition, with this conclusion. But since this is true, we obtain this conclusion. What's the advantage of this? Is that this is a quantity, this quantity here, we can control in terms of the tail of non-uniform expansion and slow recurrence. Okay, so knowing the tails of non-uniform expansion, that's what it means. So is the tail of non-uniform expansion and slow recurrence condition. It determines, so now recall, well, it's stated here. So these sets En, they decay exponentially fast. And to apply the results on decay of correlations and slow and decay of correlations in the polynomial and stretch exponential cases, we need to control this quantity. So this result says that we can control this, provided we control this, and this is unimportant in terms of the applications in the exponential case, or even worse, polynomial or stretch exponential. Okay, so En is no problem. Okay, so this is a very good theorem. It tells that we can construct, so it's essentially under the same assumptions of the previous theorem. Essentially, well, there's this S now, is strong non-uniform expansion. We obtain the Gibbs-Markov induced map that we already know it exists, and also with the control on the tail of recurrence times in terms of the tail of non-uniform expansion. Okay, so the idea is the idea of the previous one, and just observing that there is this relation between H, small h, capital H, and H theta. Okay, and so with this, it's natural to have this conclusion. So under the same assumptions, we conclude that if the tail of, so let's think of this as the tail of, the measure of the tail of non-uniform expansion, and slow recurrence condition is embedded as well in there. the tail, if the tail is polynomial, then the recurrence times decay polynomially fast. The same polynomial rate. If it's stretched exponential, then it decays stretched exponentially fast. Okay, that's very nice conclusion. This is a simple consequence of the previous theorem. And okay, well, there's a difference is that here is n plus L, but it's completely unimportant. So there's this L is uniformly bound, is a uniform constant, so it's essentially the same. So this is the existence of recurrence, the tail of recurrence times, the conclusion. And so applying the previous the theorems of the second day on the conclusions of decay of correlations, we have this first conclusion. Actually, we have many conclusions that we can deduce. I only put this one. This is the most general. Is that so? The assumption. Oops. So assume that here is elementary set. His transitive set. So the assumptions are the same. And so we know already that we have a unique SRB measure whose support coincides with mu. And again, this is as in the case we have seen before. So I don't know if this measure is mixing. So there's no hope, at least mixing. There's no hope of, in general, obtaining decay of correlations. But the consequence is that, so we all know it's ergodic. The consequence is that we can decompose this measure as we did before. So this is using previous results. We can decompose the measure into a cycle of measures such that the measure is the mean of them all, and such that we have this result. If the tail of recurrence of the hyperbolic times, this is the tail of hyperbolic times essentially, decays exponentially fast, polynomially fast, then we have polynomial decay of correlation. But as in the cases we have seen generally for these measures, that actually is a sub-measure of our good measure for the original system. And the same for stretched exponential, okay? And there are, if you go to this section 6.5, there are several corollaries where I put under some extra assumptions, we can deduce that Q is equal to 1 and necessarily equal to P, and so the measure itself. So if P is equal to 1, then the mu i's are the measure mu, and so we obtain the decay of correlations for mu. And one of the assumptions is topologically mixing. If we assume that the dynamics is topologically is more than transitive on omega, if we assume it topologically mixing, then Q is equal to 1. And so we have the decay of correlations for the unique ergodic SRB measure. Another assumption which appeared before is the ergodicity of the powers of the dynamics. If the measure mu is ergodic with respect to all powers of F, then necessarily the measure is unique. Okay, so let's apply now this to Vienna maps. So Vienna maps, well, that's the Vienna maps that Yuri has already used. So it's a family of maps in the cylinder. So in the base in S1 is DS mod 1, so it's a uniformly expanding map. In Vienna original paper, D has to be greater or equal to 16. It has to be a strong expansion. Actually, this is still an open problem to see if in general the great result would be D greater or equal to 2. And this has been improved by Boisy, Sester, and Suji, but only for open sets of maps in the C-infinity topology. Because this is only one map, but the Vienna maps is an open set of transformations, is actually a small neighborhood of this map that I described here. And they proved that we can replace D greater or equal to 16 to D greater or equal to 2 but only for open sets of maps in the C-infinity topology, not in the C3 that, as we are going to take. This is very interesting. So it's still an open problem. Can we, in the original work of Vienna, in these Vienna maps, in the C3 topology, diminish D to D greater or equal to 2? Still an open problem. So in the fibers, the vertical lines, it's a quadratic map. So in quadratic, the parameter, so you think of AS as a parameter depending on the fiber you are, and so this BS is a Morse function. So it's effectively changing with the S, and it's actually turning. So it's changing around a very good parameter for the quadratic family. So this is the original map. And we can see that there is an interval such that the image of the S1 times the interval goes strictly inside of it. So we have an invariant region. As for the quadratic, so essentially is due to the quadratic having this property. And because the parameter here is strictly smaller than 2. And then, so there is an attractor also for maps near this map. And so nearby maps also satisfy this condition. So if we change here f hat by any sufficiently close, and for this only C0 topology is enough. And so we have an attractor. I call it omega f. And Vienna maps is a family of C3 maps in a small neighborhood, in a small C2 topology neighborhood of the map described above. Well, the C3 is essentially due to the fact that it's because of the critical. So for this map, the critical set is precisely the line S1 times 0. When you change a bit the map, you change the critical line, and the C3 is to make a change of variables in order to put the critical line of the perturbations of the half hat again the critical line. It's just because of that. And the C2 topology is because we need C2 topology for Vienna calculations. And to make a perturbation and still obtain it's C2 submanifold. Okay. So what are the conclusions? Well, the conclusions are due to the original work, essentially the original work of Vienna, where, well, it's not stated there. Well, in the time Vienna proved this result in 97, at that time there was not this language of non-uniform expansion, strong non-uniform expansion, and so on. So Vienna, what actually did is he proved that there is a positive Lyapunov exponent in the vertical direction almost everywhere. But since we have strong expansion in the base dynamics, so in directions complementary to the vertical ones, we have for free a positive Lyapunov exponent in these other directions, and so actually we can prove that we have non-uniform expansion. Now, let me tell you that non-uniform expansion is in general is stronger than having all Lyapunov exponents positive almost everywhere with respect to Lebesgue measure. Is effectively a stronger condition, or at least it's not precisely correct. At least is not known if the all Lyapunov exponents positive on a set with positive Lebesgue measure implies non-uniform expansion on a set with positive Lebesgue measure. So this is the right way of saying this. So this is essentially so the strong non-uniform expansion is essentially comes from the Vienna work. Well, what I do with Vitor Araújo is put into the language of non-uniform expansion, deduced from the original work of Vienna. And also so here I say that on the attractor is topologically mixing, and as we know, this is important for the uniqueness of the measure. And this what we actually, so I proved this with Vienna in a second work. We prove that it's local eventually onto. So this is more than just being topologically mixing. So this is every open set in a finite number of iterates becomes the whole attractor. And in the work with Vienna, this from 2002, we proved that. So we have an open set of transformations. So applying the previous result, let me just derive the conclusion, is that so applying the previous results, we have that there is a unique SRB measure whose support is the attractor, omega, I called it omega. And moreover, we can prove that the basin covers almost every point so this is the basin of the attractor, S1 times this interval. So we can prove that, well, the measure in the attractor is a consequence of our previous results, is unique, but we can actually prove that the basin covers almost every point in S1 times I. So it's a very good measure, given the conclusions for almost every point of physical measure for almost every point in S1 times I. And well, we have this tail. This is what comes from Vienna's work, that we have stretched exponential tail of the hyperbolic times. And so via our previous results, we deduce this. Let me tell you that the decay of correlations has been deduced by Guezel first. Here is a consequence of our results. So Guezel used slightly different, well, the ideas of Guezel, that's the ideas that we use, but slightly different approach in the line of what I told about the work of Pinheiro, so global construction and so on. But he proved that. We have proved before with Stefano and Pinheiro super polynomial decay of correlations, and then Guezel improved our result. And in my work with Vienna, we proved that the measure, the SRB measure, so that's what I was saying, the SRB measure depends continuously. So the density in the L1 norm depends continuously on the map in the open. So we have an open set of maps. So that's what we call statistical stability. So we have these very nice properties for these Vienna maps. This has been this example of Vienna maps have been very inspiring for many of the things we do for non-uniformly expanding maps. It remains an interesting open problem to know if this estimate here above is optimal for these Vienna maps, or just a limitation of the method that Vienna used. It's still an open problem. Why stretch exponential? Why not exponential? So that's a very nice problem, open problem. So with this example, I finished the non-uniformly expanding, the case of non-uniformly expanding maps. And now to finish my course, I'm going to consider partially hyperbolic attractors. So the ideas and objects are similar to this non-uniformly expanding case. Now we'll have a strong contracting direction, and we'll have another direction. We'll have an invariant splitting. So that's my next goal. And we'll have, so assume we have a further invariant compact set on which we have a splitting of this type. So splitting means invariant by the derivative, these sub-bundles, ECS and ECU. And assume it's a dominated splitting. Dominated means this. So this is a condition used by many people, many results. So this says so. In the beginning, I'm not assuming contraction or expansion in these fiber bundles, but this says that, so the idea is that the behavior in ECS is essentially contracting behavior, and the behavior in ECU is essentially an expanding behavior in the following sense. So so this condition says that not necessarily, so if we have strong contraction here in ECS, we don't need to have contraction backward in the ECU direction, or if you prefer, expansion in ECU direction, because we can compensate any non-contraction here by a strong contraction here. Okay, so this is the idea of splitting, and vice versa for the other case. So it says that not necessarily contracting, but not necessarily in doing what it does when it's a uniformly hyperbolic decomposition, but when it does not what is expected to do, the other direction compensates. That's the idea. And then we say that ECS is uniformly contracting if this holds. So this is the usual contracting property, and uniformly expanding if this holds. So this is the usual uniformly expanding property. And see that if both are uniformly, so if ECS is uniformly contracting and ECU is uniformly expanding, this is the classical uniformly hyperbolic situation. When one of them, when ECS or ECU is uniform, so the behavior is uniform, we drop the C. So C here stands for center stable, center unstable. So when we drop the C means is, as in the classical situation, is stable or unstable. It contracts uniformly or expands uniformly. So this is just simplifying the notation. And we say that it's partially hyperbolic. So above I defined having a dominated splitting. The set case is partially hyperbolic if it has a dominated splitting for which one of them has the uniform behavior. I mean, for every point in the set K, either ECS is uniformly contracting or ECU is uniformly expanding, or both hold, but it cannot be for certain points is one of them. No, it's for every point, either ECS is uniformly contracting or ECU is uniformly expanding. Okay. Well, we say that omega is an attractor. Well, if the usual condition holds, there is a neighborhood on which the image is sent onto the interior of that neighborhood. And so the attractor is the intersection of the Fourier images. So we have, according to my definition of partially hyperbolicity, we have essentially two situations. The first one we are going to treat, and the one all these methods I've been describing can be applied, is for this situation ES, so uniformly contracting, plus center unstable. There are results, and at the end of this presentation, I will mention some results in the other situation. So the other situation is ECS plus EU. There are several results on the existence of SRB measure and decay of correlations. But interestingly, in the dual situation, not the one I'm going to treat here, the construction of the SRB measure is much simpler. Because so the SRB measure essentially lives on unstable manifolds. If we have strong non-uniform expansion, then essentially is using a result that I've already mentioned by Pezin and Sinai, on which essentially is the classical situation. We take Lebesgue measure, iterate forward control, the push forwards, and we have an SRB measure. And so constructing the SRB measure in the other situation, not the one we are going to consider here, it's easier. But interestingly, proving decay of correlations for the other case for which constructing the SRB measure is easier is much more complicated. There are only some partial results. So I'll try to have a time for, at the end of this presentation, mention those results and tell you the situations on which we have those results on decay of correlation. So let's start now with this situation. And naturally, we are going to consider along the center unstable direction, we are going to consider some non-uniform expansion. And again, I'm going to consider a weak version to deduce the existence. So this is this with lim-inf here, and I don't know why I cannot highlight. No problem. So with lim-inf here, and later for the decay of correlations, we will consider lim-sup. And again, we introduce hyperbolic times. Well, see that this is the condition along orbits, but of course in the ECU direction, which is natural. But this condition is essentially the same as we considered for the endomorphism case. And also introduce hyperbolic times is essentially the first condition in the hyperbolic case, in the non-uniformly expanding case. Here we don't have, so we consider diffeomorphism. So actually, there are generalizations of these results for cases of diffeomorphism, but out of a set that there might be discontinuity points, but I'm not going to consider that situation. It's using similar ideas of non-uniformly expanding maps with critical sets, so we can do that. But here I'll stay at this level of globally a diffeomorphism. And the hyperbolic times are introduced similarly. And so here is a direct application of Ple's lemma. We obtain the existence. So whenever we have this condition, we obtain the existence of a positive fraction of hyperbolic times. So this is Ple's lemma essentially. Now we have some more complication, not due to the diffeomorphism case. So we have more directions to control. And a first one is that, okay, so assume, the first one is that we can introduce some number such that this is essentially uniform. So this condition here, this condition is very important. This is essentially uniform continuity of the first, of df. The uniform continuity of the df allows us to introduce a delta 1 such that whenever the distance of a point to x is at a distance less than 1, oh, the condition, so this is, I didn't introduce them, I forgot. The condition of partially hyperbolicity, actually the dominated splitting, allows us to introduce invariant cones. So this is as in the classical situation. In the classical situation, to introduce the cones, we don't need the hyperbolicity, we just need dominated splitting. And this is the center unstable cone. And so, so we have naturally this quantity here appears. So the df at a certain point in the ECU direction. And so I'm telling that, so see that sigma to minus 1, 4 is a number bigger than 1. So I'm saying that in a neighborhood, the derivative of any other point, so see, this is for fx, so this is why I take fy. So the derivative of any other point is close to the derivative of this point f of x, but not only for tangent vectors, but also for vectors in a cone field, because the slope of the cone field is we can take it very small. And so this is just an argument of continuity. So we have this good estimate. So, this is the proposition giving us the good neighborhoods to VNs. So this is similar to what we have obtained. So here we have to take CU disks. So CU disks is disks where the tangent space is contained in the center unstable cone field. So for points in the CU disks, if a point in a CU disk has a hyperbolic time, and here there is some complication because in the previous case, I always consider sigma hyperbolic times. And I could avoid this, but I want to tell you something very subtle, which has to do with the HN stars and the HNs. So this is the case where we need to introduce HN star, and it has to do with these hyperbolic times. And see that sigma hyperbolic times are better than sigma to any power smaller than 1 hyperbolic times, because sigma is less than sigma to 1/2 or sigma to 3/4, and sigma is the rate of contraction. Okay, so I'm telling that if it's and this is better than this, so sigma to the 1 is better than sigma to the 3/4 is better than sigma to the 1/2. That's the idea. And if we have this intermediate sigma hyperbolic time, sigma to the 3/4 hyperbolic times, then we have the good conclusion, the good neighborhoods in the disk. We have them expanding because we have sigma hyperbolic time. Well, we lose something in the hyperbolic time. It's no longer sigma to the 3/4, but it's sigma to the 1/2. And we have, so the expansion and the good distortion control. So modulo these details on the sigma to the power. This is essentially the previous lemma of endomorphism case, now for CU disks. And so we can deduce as before the composition. So this is a theorem similar to the previous situation where we decompose. So if we have a partially hyperbolic set and we have a set with positive measure where we see non-uniform expansion along the center and stable direction, then there is a finite number of transitive sets attracting almost every point on the set H. So this condition holds. Moreover, this is parallel to the previous result for endomorphism. Moreover, each of these attractors contains a CU disk on which F is non-uniform expanding along the center and stable direction for almost every point in the CU disk. So the idea, actually, this theorem was proved first than the other one. The other one I've decided to include in the book in the endomorphism case, but we proved it directly in the diffeomorphism case with these co-authors of mine. Okay, so this is similar to what we have seen before. And so now we consider, again, I'm going to consider one of these transitive pieces and one of these disks that we know exist in the transitive pieces where we see non-uniform expansion in the center and stable direction for almost every point in the disk. Again, we consider hyperbolic times and so on. Well, there's this difference here. Well, I consider the sigma 3/4 hyperbolic time. Well, this is completely unimportant at this level. The important thing is that we have some number smaller than 1, sigma to something is okay, and we have this. And we have this concatenation property as we had before. So this is simply the definition. And actually, here is sigma hyperbolic time, but I define the HN. So here is sigma hyperbolic time, and we know that we have this, since we have the strong assumption is, here is only still not the decay of correlation. It's only to build the SRB measure. I'm taking the weak assumption. Since it's the weak assumption, we obtain the weak frequency. Okay, this is lim sup greater or equal to theta. And I define this sigma for if we fix a sigma hyperbolic time, then we have this. Then we consider Hn as the set of points which have a weaker sigma hyperbolic, a weaker hyperbolic time. So it's sigma to the 3/4. For this Hn, we have this property. And notice that sigma hyperbolic time implies sigma to the 3/4 hyperbolic time. This is because it's more, so sigma is smaller than sigma to the 3/4. And so we can use the same ideas and build a partition and use. So the idea here is to check the conditions of our very first theorem of today. But now I'm not, so what is the idea? So we take a disk and we use these VNs as the first, so VN satisfy the first assumption of our very first theorem of today. And we build these neighborhoods that grow to large scale. And then we use the transitivity to bring them back. But now in this situation, bringing back is not as before, because before it was going a certain part diffeomorphically onto the delta zero. Well, now coming back is coming to a disk, which is, this is a diffeomorphism case. It doesn't need to come exactly onto the delta zero, the disk delta zero. So it comes close to delta zero, but is another unstable disk close to delta zero. And you take another domain, another VN, it grows to large scale, and it comes to another disk close to delta zero. And so we build the first generation, the very first generation. So this idea here is similar to the idea we used in the last day for the solenoid with intermittency. We can build a Young structure using this idea of generations of disks, of unstable disks. So we start with these VNs, grow to large scale, use transitivity, and we bring them back, and we build a second. So the first generation is the disk delta 0 itself, and then we build more generations of center unstable disks. So the idea is that one. So it's similar to the construction of the solenoid with intermittency. There's only one point, is the integrability. So the integrability, this is the conclusion. So under the assumptions that we have above, then F has a set with a full Young structure. See, full Young structure is the disks themselves, they are contained in the set lambda, which has a Young structure. So this in general doesn't need to be like that. So in general it's only a product structure, but in the unstable manifolds has a set with positive measure. Here is the full disk is contained. So this is a special situation of attractors because we are considering some attractors. And but the integrable recurrence time. So the idea is to use the theorem 4.1 in the second condition or third condition, the I3 in the last number of iterates. There in the theorem it was free, so it doesn't matter how we are going to obtain that, provided we have some properties, we have some conclusions. So here I'm telling you that we have to be careful when we return, we use transitivity, but we construct this Young tower under again some algorithmic construction in order to obtain that Young structure. What about the recurrence times? Well, you may say, well, but we have obtained the integrability of recurrence times under the assumptions of the theorem. Well, under extra assumptions, because we use the concatenation property, which is here, but we use the strong positive frequency of points in a certain set, and the concatenation property is with respect to a Gibbs-Markov map. So in that place where we deduced the integrability of the recurrence times, there was a Gibbs-Markov map. And the problem, okay, you may say, well, but here we have a Gibbs-Markov map as well. We have the quotient of the recurrence map. Well, that's what I put here, that quotient that I have introduced last day. And this is the Gibbs-Markov map, this capital F. But the problem now is here, is that the concatenation property here, and that's why I consider this 3, 4, 1/2 and sigma to the 1, is due to this fact. The fact we have this concatenation property for hyperbolic times. The problem is that when we go from X to FR of X, so is the return to the Young structure. Okay, if N is a hyperbolic time for X, N bigger than R. If N bigger than R is a hyperbolic time for X, then N minus R is a hyperbolic time for FR. Okay, this is what it says here in property 67 above. But we want the concatenation property not with respect to this F, but with respect to the induced dynamics, the Gibbs-Markov dynamics F. So I've used properties of the Gibbs-Markov map in the proof of that proposition that gives the integrability. So we have a problem. The concatenation property is no longer true because then I replace this point FR of X by the point here down. But the point is the following. When I build the Young structure, I build in a very small region. Small region in such a way that we have this property here, small in a neighborhood of size delta 1, in such a way that this property here holds. And so we can see that estimates on the derivative of a point to any point which is close to it losing 1/4 or sigma to the minus 1/4. And that's precisely why I consider first, I'm not going to check all details, but just recalling you that we used sigma to the 3/4. When we lose 1/4, we go to sigma to 1/2. And sigma to 1/2 appeared here as well. Okay, so that's the idea. But we need to change the set for have the concatenation property. And so that's why I consider the Hn star a stronger version of hyperbolic times with a sigma. And with this stronger version, I have the concatenation property because I choose the size of these stable manifolds small in such a way that it's contained in the good neighborhood around the point in which you can control the derivative of any other point in terms of the derivative on the point on the point x, or iterates of the point x. And so we have this. This is this tells us that Hn star is a frequent sequence of sets. Well, this is because of this. And moreover, we have the concatenation property. This is the concatenation property, or implies the concatenation property. The concatenation property is that if you take x in Hn star, then the image under the Gibbs-Markov map necessarily belongs in Hn minus the recurrence time. Well, it's something like that. Okay, so this is the point where we need to change the set, because we cannot prove that the same set, if we consider with respect to the same hyperbolic times, we cannot prove the concatenation property. Fortunately, the proof of that proposition holds with the weaker version of the concatenation property. And so with this, we can prove the integrability of the recurrence times, and applying it. So we have a Young structure with integrable recurrence times. We deduce the existence of SRB measures. And to finish, so this is to finish this ECU plus ES case. For decay of correlations, again, we need stronger version. We need lim sup. We can again introduce this. And we have again, under the assumptions which are similar to those we had before, then we have a unique SRB measure to support is the attractor. But then again, we don't know if this measure is exact. And so we obtain a decomposition of it into a finite number of measures, and we obtain the good conclusions with respect to these measures. And again, under some topologically mixing properties or ergodicity of all powers, we deduce uniqueness. Okay, and there are also examples. No, I'm not going into that. So this is the results for partial hyperbolic attractors. And to finish, just 2 more slides. The dual case. This is just to mention results. I think it's fair to mention them. That deserve to be mentioned. Any question?
Question.
What?
A question.
Oh, please.
So what should I think about when, as examples of these partially hyperbolic systems, does the time one map of a flow fit into this framework?
Sorry? So examples of systems like this?
Yes.
In my paper with Vian and Bonatti, we introduce, so it's a derived from Anosov. If you go to, so you take an Anosov, you go to a saddle point of the Anosov, you have to take the unstable direction, the dimension greater or equal to 2. And so you can make some damage in the unstable manifold in order to create a non-uniformly expanding map in that direction. So you create an invariant direction with contracting in the unstable manifold of the attractor, of the Anosov diffeomorphism. And so you create that's what we call a derived from Anosov, such a way that the center unstable direction was the previous unstable direction. But since we have there a stable contracting direction, it's no longer uniformly expanding. But in average, you can make a calculation. If the Jacobian near that saddle point is strictly bigger than 1, the frequency of visits to that point is small, and so we still have non-uniform expansion in the center unstable direction. So what we had in mind when we proved these results word is derived from annals of diffeomorphisms. Okay, but we can also apply to if you think of the Poincaré map for the Lorentz geometric flow, we can also apply these ideas to that situation. I think you mentioned flow. Was that the question?
Yes, I was mentioning time one map of flows, but
for time one, well, we can try to apply. The problem is that if you want to deduce the results for flow, is more delicate because, well, that's Dolgo-Piat techniques, and more people have used this, and we have problems also with the flow direction for the mixing. But for time one, there are flows for which these assumptions are verified. Yeah, for the time one, at time one, it's no problem. We obtain partially hyperbolic systems like that, like this. Okay?
Okay, thank you.
So these are the examples I was not going to talk about, but thank you since you asked. So I mentioned them. So let's go to the dual situation. I think it's fair to mention these results. As I said, constructing, so the dual is now, we have uniformly expanding direction and center stable. And so constructing SRB measure is essentially iterating Lebesgue measure. So we have unstable manifolds. Classical constructions also work in this case. We have unstable manifolds. You take Lebesgue measure, iterate on an unstable manifold, control the push forwards, the densities, and you can construct ergodic SRB measures. Then Viana and Bonatti, they proved the result saying if we have an attractor for which the center state with, here is a mistake. Here is not CU, is CS. Mostly contracting. So here should be CS, mostly contracting. So what is mostly contracting? Mostly contracting is, so this is positive, this is negative. So this is the biggest Lyapunov exponent in the center stable direction, this lambda C plus. We say the ECU is mostly, I don't know why I cannot underline, I highlight. So we say that ECU is mostly contracting in that direction. If we have all Lyapunov exponents negative in that direction, so that's what it says, for positive measure subset of points in any unstable disk. Okay, for any unstable disk, there is a positive Lebesgue measure set of points for which we see all Lyapunov exponents negative in the ECS direction. So again, there's a mistake here. This is ECS, is mostly contracted, it's not ECU. ECU here is EU. So it's my habit of writing ECU. I wrote ECU for ECS, okay? So, and Vian and Bonatti, they proved, so they use this work of Pesin and Sinai, and they give sufficient conditions for the basins of the topological basins of the attractor, almost every point belonging in a finite, so belonging in the basin. So there is a finite number of measures such that the topological basin of the attractor is contained in the union of the basins of those SRB measures. And moreover, they give sufficient condition for the uniqueness of the SRB measures. And the condition if the leaves of the unstable foliations is if any leaf of the unstable foliation, so the global unstable manifold, if it's dense in the attractor, if that is dense in the attractor, then there is only one SRB measure. Okay. So the result of Bonatti and Viana is essentially a result of finiteness and uniqueness so conditions for finiteness and uniqueness of SRB measures. And decay of correlations. Well, for decay of correlations, I mentioned here 3 results, but you see that it's only in partial solve the problem. So we would like to have, so assume we have an attractor of this type, and we have some contraction in the CS direction. can be non-uniform contraction, similar to what I've considered, but now instead of f-1, you take f, or even this is a weaker condition. So maybe the other one stronger can be a first attempt. Would you like to have assume some strong non-uniform contraction in the ECS direction and deduce similar results for the decay of correlations? Well, we don't have that result, and the results we have are this one. I don't know, to be honest, I don't know if there are any recent results in this direction. The only ones I know for this kind of attractors are due from the beginning of this century, due to Dolgo Piat and to Armando Castro. Well, you see, the first result is by Dolgo Piat, is for three-dimensional manifolds. So not very general. And moreover, the ECS has to split into two sub-bundles, one uniformly contracting and the other one mostly contracting, the sense I defined before. Then, in this situation, he proves that the SRB measure, the unique, so we assume that unstable manifolds, so this is all for unstable manifolds being dense, so there's a unique SRB measure. And so he proves that the unique SRB measure has exponential decay of correlation. The second result is due to Armando Castro. He starts with something of the type I've just mentioned, the derived from Anosov. It starts with an Anosov and it goes to a fixed point, it makes some damage. That example we introduced, we considered in fact, this kind of examples have been used before by Magné and I think by Bowen. So many people use this kind of derived from Anosov. The derived is not always the same, but the idea is always the same. And so Armando proved the decay of correlations for those derived from Anosov, but using in a strong way the existence of a finite Markov partition. So it makes some perturbations of Anosov, but the perturbations have to be done inside one element of the Markov partition in such a way that the Markov partition still exists for the perturbed system. And he uses this in a strong sense. So still very particular situation. And the other situation that Castro considered, so it could forget the Markov partition, but the price to pay is that the center stable direction is only one dimensional. And in all these cases, the conclusion is exponential decay of correlations. But you see that the cases are very particular. The argument of Dolgo Piat is not inducing schemes. The argument of Castro in both works is using these Young towers, but he does a very nice inducing scheme because he does the inducing scheme in the stable direction in backward time to build the inducing scheme. But he's still using Young results that I've mentioned here. The result of Dolgo Piat is using different techniques, I think standard pairs and things like that. Okay, so that's all. Freedom now, especially for you. Thank you very much. And I leave you with a lot of references. I'm going to the very first page. So this very first page has this new link of today, which goes to these full notes. Okay, so you have here the link. And thank you very much. Are there any more questions?
Actually, I wanted to make a comment that you do some kind of essential use of the hyperbolic times, right? Places,
yes.
returns, and if you want like exponential decay, you assume positive frequency in some way.
Yes, we need a positive frequency. See that I use the positive frequency in two ways. For the decay of correlation in a strong sense. That has to be after a certain, for most points, after a certain threshold, depending on the point, it's positive frequency forever, okay? For every time. And and the decay of correlations is given by the decay of those thresholds. So the points that need more time to achieve this positive frequency, strong positive frequency. I also used positive frequency to build the SRB measures. A weaker version of positive frequency is that for any large n, we can find arbitrarily large n such that at that n we have positive frequency. But then maybe for a long time we don't see more n's with positive frequency. But again, in the future, eventually a new n appears with the same positive frequency. So I have positive frequency in two ways. And the second one, the first one I've described now is what I call strong positive frequency. But I use, as you say, I use the hyperbolic times in a very strong way to build these VNs. They are essential in all these constructions. And the frequency of those hyperbolic times are also very important.
So only assuming the presence of these infinitely many hyperbolic times without saying anything about the frequency, you can get the Young structure.
Yes, but not the integrability of the recurrence time. Mm-hmm. I use the weak version of positive frequency to deduce the integrability of the recurrence time. So if you don't want integrability of recurrence times, you don't need positive frequency, any kind of positive, just for almost every point has infinitely many hyperbolic times. It's enough. That's what I did here today.
So the parallel I want to make is that in the symbolic dynamics construction, we also require some presence of hyperbolic times.
Okay.
So the set that we code is a kind of subset of hyperbolic points for which you kind of return to the same passing set infinitely often in the future and in the past.
Okay.
So we see this as a kind of a it's not directly a hyperbolic time because hyperbolic times is stronger, right? You have to have those contractions in the past.
But still has some hyperbolicity of that type.
Yes, some sort of good, almost uniformly hyperbolic.
I didn't mention that result, but I think Stefano with Pesin and Klimanaga, they use that idea to build inducing schemes.
The idea of symbolic dynamics, you mean?
Yes, they use these Pesin blocks.
Ah, okay. Okay. I see.
So it's in between our approaches. There's this work of the approach of Stefano Luzzatto, Klimanaga, Luzzatto, and Pesin is inducing, but uses a lot these Pesin blocks.
Mm-hmm. Okay. Still going in the direction of positive frequency. So on the symbolic side, you can also have that. And I think that's exactly what Bouzy, Crovisier, and Sarig are going to do next week. So they have this coding, and then to get exponential decay, they have, in some sense, to prove some positive frequency of good times.
Okay. And
so
it's tails, maybe.
Yeah, very much related to what you spoke today.
Yes. That's great.
Thanks.
So see you next week. Have a nice weekend.
So does anyone have any other question? I don't think so, perhaps.
Okay. So if not, let's finish.
Yeah.
Bye-bye.
Thank you.
Thank you, Zé. So I'll see you all next week for the workshop.
Yes.
That it's exactly at the same time.
Bye-bye.
Same time slot, but every day. Bye-bye.
Every day.